So and then for turbulent boundary layer, okay, so we have two common methods. One is called one is, okay, let's say, yeah, I'm talking it's here. So this is just the idea of turbulent boundary layer. So as I said, so we have a flat plate here. So we have a flat plate here. So and then so the laminar boundary layers occur, and then we have a transition here, and then it will become turbulent boundary layer. And as you know, the turbulent boundary layer, it has a lot of chaotic velocity profile. So and in this transition, so only a few of them is chaotic, but in laminar, the flow will flow in very lawful manner, a very good streamline. So, and then in these topics, we will also discuss the difficulties to about the turbulent boundary layer is if the boundary layer is 100% laminar like this, so we could use the von Karman solution and also the Blasius exact solution. Then if the speed is too high, so then we could assume that all boundary layers that we have here is actually in turbulent condition. So then we could use the idea of turbulent boundary layers. So then in between condition, so for example, we have a flat plate here, but 50% is laminar and another 50% is turbulent boundary layer, then we need to have another idea to solve the problem of this one. So, and then for this situation, actually what the final product, the final numbers that most wanted by researcher, first is the boundary layer thickness here. Okay, so we have this one and this one. And the another one is the value of CD or the value of FD. So because the mean CD or CL and also FD or FL. So in this situation, we will get the value of CD. We focus on CD because for lift force, coefficient of lift and coefficient force, lift force and coefficient of force is using by the aeronautical one. So to get this one, normally we try to input the idea of Mach number and so on and so forth. Because as you know, flight aeroplane cannot take off if it's not reach certain speed, certain value of speed. So mean just a low speed cannot create enough lift force to lift the aeroplane upward. Okay. So we are focusing on drag force because you know in UTM we have aeronautics department, so aeronautic panel, so they will discuss about that for the lift force. Focus on for the lift force and the lift coefficient. So for fluid mechanics, we are trying to focusing on application that occur around us. So we have just a very not so high velocity, and we are focused on the drag force because drag force is actually a resistance for us when we move at certain velocity. Okay. So this is just for the our revision. So in laminar boundary layers, we assume that the velocity profile. So the velocity profile here means the velocity profile inside the boundary layer. So mean at this one. Okay. So it's refer the ratio of the velocity inside the boundary layer here with the velocity of the free stream velocity here. So this is the small u. So, and this is the capital U. Okay, I will write U as U over U like this one. So I think I put this in your assignment so you know what to do. So we have the most common one is this one. So we have by the power of 1. So we have second order polynomial, we have third order polynomial, and we have a quartic here. So and then we have a sinusoidal. So in your assignment, you need to prove how to get the this velocity profile and also this and also this. Okay, you need to prove it because in one of my lecture I show you how to prove this velocity profile. Okay, so this is for the laminar region. So and then if the question didn't give you any velocity profile for the laminar boundary layers, what you need to do is you could use Blasius. Okay, if a velocity profile is not given, so please use Blasius exact solution as the representative of the laminar boundary layers. So means you could directly calculate the value of delta by using 5x over square root Reynolds, because this is the equation proposed by the Blasius. Okay. So and then we are going to evaluate. So in this term, in this first part, we assume that we are evaluating 100% turbulent boundary layer. Like the previous part, we are evaluating by assume that 100% is laminar, and now we're evaluating 100% is turbulent boundary layer. So we have two methods. One is the power law form, and another one is the empirical form. Both have this advantage. Okay, so the advantage is the power law form is easier, but it is a little bit less accurate compared to the method number 2. And for the method number 2, it's more complicated because it asks us to calculate so many things. So, but the answer is accurate. So it's depend on the application that we use. So sometimes the power law calculation is quite okay. It's acceptable value for the analysis. Okay, so this is what our assumption here. So we assume that it is 100% turbulent boundary layer. So we start with the all of the here is turbulent boundary layer, or you could assume that laminar boundary layer actually occur immediately at the front here, and then immediately it change into turbulent. So means the existence of laminar boundary layer here can be ignored. So we could assume that all the region is in turbulent boundary layer. Okay, so, in tutorial we will see that the influence of laminar and turbulent boundary layer. So for the calculation of rho E, for calculation of Reynolds number, so the idea is still the same. So we are using rho U X over mu, or sometimes we write as rho U L over mu, which is the X or the L here actually the length, the x-axis length of the object here. And then the U is, the rho is the density of the fluid. The U is the free stream velocity, the X is length of fluid plate, and the dynamic, and mu is the dynamic viscosity of fluid. Okay, so what is the power law? So for power law, the idea is we assume that velocity profile in the turbulent boundary layer can be represented in terms of this one. So this is the law. So the power law, because we assume that the velocity profile means that if we have a flat plate here, so we have the boundary layer here. So let's say the boundary layer here is turbulent. So the velocity profile inside this turbulent boundary layer can be represented by using this equation. So it is U over U, which is the small u here is the velocity inside the boundary layer here, and the capital U here is the free stream velocity here. So the same idea with the laminar boundary layer. Okay, but we don't have any plus something or plus something. So means that it will not have that kind of velocity distribution. The velocity distribution only occur in this term, 1 by the power of 1 over n. Okay, please do not confuse with this one. So mean the velocity distribution, velocity profile for turbulent boundary layer is shown in these terms. So 1 over n here. So the value of n here is actually depends on the velocity of the free stream velocity. So for example, n over equal to 7 is usually used if the Reynolds number is like this one, means around 5 times 10 by the power of 5 to 10 by the power of 7, and between 7 to 8, so we have n power of 8, and between 8 to 9, so we have n is equal to 9. So this is, it's depend on the situation. So and then, so this is the most important thing that you need to understand. So if you see the solution in a boundary, in laminar boundary layer, so we will use the von Karman solution, von Karman shear stress calculation by using the von Karman. Tau is equal rho u square d theta dx. So and then we need to compare with another value of tau, which is tau equal du dy at y equal to 0. This is the shear stress calculated from Newton viscosity of law. Okay. However, in turbulent boundary layer, we found that, for example, we substitute the value of, let's say we have u over u is equal y per delta by the power of 1 over 7. If we do du dy and then we substitute the value of y equal to 0 here, so we get the value of 0. So here, your mathematics calculation is correct, but it will ruin the calculation of turbulent boundary layer. Mean the number 0 here is actually cannot be used to continue the calculation of boundary layer. So what we need to do is, first, bear in mind that Newton viscosity of law is cannot be used in turbulent boundary layer. So as a replacement, we need to calculate the value of shear stress here by the empirical method introduced by the Blasius. And this one is actually will be given in the question, because you need to do the numerical or you need to calculate, depends on your experimental works. Okay, so means here to solve turbulent boundary layer, so you need value of shear stress by the empirical one, by the Blasius calculation. So normally we will give you the value in the question. Okay, let's say, so the most common velocity profile for turbulent is called 1/7 power law. So 1/7 means here the power for y over delta here is 1/7. So this is the common velocity profile for turbulent boundary layer. So it is mean that if you have situation of turbulent boundary layer and the velocity profile is not given, so you could immediately use the idea of 1/7 power law. So for laminar boundary layers, if the velocity profile is not given, you could use a Blasius. For turbulent, you could use 1/7 power law. Okay, now we evaluate the 1/7 power law. So as I said, we cannot use Newton's law of viscosity to calculate the shear stress, because it will give us 0 in value. So we need to get the shear stress based on the Blasius calculation. So normally we will give you in question. So let's say for y over delta by the power of 1/7, the shear stress is actually given like this one. So 0.0226 rho u square mu over rho u delta by the power of 1/4. So in certain textbook, they will give you mu over rho u and delta, but in certain textbook, they will give you nu over u delta. Okay, so please know that the mu is equal to rho, No. So by using this relation, so we could change the terms of this one into this term. Okay, please be careful about this because previously in certain tutorial we use a lot of nu, the kinematic viscosity, but might be in this node we will use the mu in our notes. So first, we calculate the boundary layer thickness. So the equation for boundary, okay, so we start with the theta here. So the momentum thickness, according to our previous calculation, it is equal to this equation. So we have u over u, 1 minus u over u dy. So what you need to do is you substitute the value of u over u here with y over delta by the power of 1 over 7. And then you solve the integration process here. So you will get it is equal to 7 over 72 delta. So this is the value of theta. So and then we substitute the value of theta here into the von Karman equation. So we know that von Karman is here. Tau is equal rho u square d theta dx, and then we substitute the d theta here. So it becomes 7 over 72 delta. So and then we could get this term. So we cannot do more. We cannot solve more this one. So we leave it as equation number 1. So what we do is, again, we cannot use this Newton law of viscosity because it will give a value of 0. And the shear stress is equal to 0 is not showing the real situation, because in no slip condition, the shear stress is maximum at y equal to 0. But what we need to do is we need to get the shear stress obtained from the result of Blasius solution. So it is given in the question. So tau from Blasius solution is 0.0226 rho u square mu rho u delta 1 over 4. So what we need to do is we equalize these both equations. So this is from the von Karman, and this is from the Blasius calculation. So and then I think you could assume you could do the calculation. So we bring the dx to the right side. So and then we bring the delta here to the left side. So and then we solve the now we get this term. So however, we still have delta d delta here and d dx. So what we do is we integrate both sides here. So and then we integrate them, so we get this term. So after integration, so we get a constant here. So we check the constant whether it has numbers, it has value or not. So we say at x equal to 0, so delta is equal to 0, then c is equal to 0. So this boundary condition is actually based on this diagram. So let's say we have a boundary layer there. So at x equal 0 here, so for sure the boundary layer is not exist yet, so the delta is equal to 0. Then we substitute into the equation, we could get that the c is actually equal to 0. Now we will have this term, okay, because the value of c is equal to 0. So then if we simplify this term, so finally we could get the value of delta here is equal to 0.3721x over ring dot number by the power of 1 over 5. So and then we could calculate the delta star. So by using u over u equal to y over delta 1 over 7. So we substitute the equation for the delta star here. So we get is 1 over 8 delta. So we substitute the value of delta here with our previous calculation. So finally we could get this value for the delta star. So and then again we could determine the momentum thickness. Previously we get each 7 over 72 delta. We substitute the value of delta and then we get this value for the momentum thickness. And then shear stress. So again, so we have shear stress from the Blasius solution. So we have a delta here. So we substitute the value of delta, then we get this term as our shear stress. So here we are not using the shear stress from the Blasius calculation because we still have rho u square d theta dx. We cannot use this because we have the unfinished business here, so that we have the still in differentiate mode, in differentiate condition. So the answer is the same if you solve the problem of d theta dx. You need to integrate both sides, and then finally you will get this value. But to ease your calculation, you are advised to use the shear stress from the Blasius solution. And then the drag force. So the drag force, the equation is this one. So it is integral from 0 to L for tau times B dx. So B dx means the area. Okay, so let's say we have the flat plate like this one. Okay, so and then for a small area here, so the area here is B is the width, and the distance here is dx. So B times dx is the area. So and then we substitute the value of tau here. So we have the B and the x, and then we integrate from 0 to x. So here, please bear in mind, in Reynolds number, so we know that Reynolds number is rho u x over mu. So you need to expand the Reynolds number here because Reynolds number has element of x. So you need to integrate this x because we are integrating with dx here. So first you need to expand the Reynolds number. So you integrate the terms. So and then finally you could get this term. So mean the b will remain as a constant. So and then for the drag coefficient, so this is the common equation. So normally we write as Fd is equal to Cd times 1 over 2 rho a u square. So and then to get the value of Cd here, so we have drag force over 1 over 2 rho u square BL. So we know the value of drag force here based on the previous calculation. So we get the CD is equal to 0.0722 over Reynolds number by the power of 1 over 5. So this is actually the basic calculation for the turbulent boundary layer using the most common velocity profile, which is we call it as 1/7 power law. So which is equal to U over U equal to Y over delta by the power of 1 over 7.